Hello, welcome to lesson 2 of complex analysis. In this lesson, we're going to cover the polar form of complex numbers, and then an extension of that using the exponential function. We'll also talk a little bit about graphing the complex numbers in terms of the polar format. We'll do Euler's formula, which is quite interesting. And then we'll follow with the derivation of a trigonometric formula using Euler's formula, and then we'll finalize with a few exercises. I should point out that this lesson assumes a background in trigonometry as well as a little bit of calculus. We talk about limits in this particular lecture. The polar form of a complex number is basically a representation using the length of the complex number from the origin, which is called the modulus, and the angle that the complex number makes with, or the vector that the complex number makes with the x-axis. So we can see here in the figure, we have z equals a plus ib. That's our complex number. The angle it makes with the x-axis is theta, and then the modulus is just a squared plus b squared. That's from the Pythagorean theorem. On the right, we have b represented in terms of the modulus and the sine of theta, and then a represented as the modulus times the cosine of theta. And the polar form is what we have written here. Z equals the modulus times cosine theta plus I sine theta. That just follows from how we've labeled or represented the A and B parts, the real and imaginary parts of the complex number. A lot of times the text will use R instead of this notation here. So I'm showing both, but I think I'll normally be using this one on the bottom. Let's do a couple of examples of converting a complex number from a Cartesian form to a polar form. So on the left, we have the complex number 1 plus I. We put that on the graph. You see that the x distance is 1, the y distance is 1. So we have an isosceles triangle. This is 90 degrees, which means these other two equal angles need to be 45 or pi over 4. So we already know the angle required to convert to polar is pi over 4. And then the modulus is, again, by the Pythagorean theorem, is the square root of 2. So we just plug into the formula. And this here that I'm highlighting is the polar form. If we substitute in the value of cosine pi over 4 and sine pi over 4 into this formula, we get this line here. And then multiplying by the square root of 2, we come back to the original format for the complex number. So this line here is basically a cross check. Okay, then going to the right, we have another example. The complex number is 1 plus the square root of 3i. So the y distance is square root of 3. The x is 1. Using the Pythagorean theorem, the hypotenuse is 2. You'll recognize this from trigonometry is a 60, 30, 90 triangle, and so we have all the information we need. We just put it into the equation here. Z equals 2 times the cosine of pi over 3 plus I times the sine of pi over 3. And again, we can do a cross check by putting in the values 1/2 for cosine pi over 3 and square root of 3 over 2 for the sine of pi over 3. And if you multiply 2 times that, you come back to the original. So we've checked our solution. The parameter theta is often referred to as the argument of z. And the problem we have here is that the argument of z is not unique. So if we have, for example, 45 degrees or pi over 4, then every 180 or 2 pi radians, we either plus or minus, we come back to the same value. And that gives us multiple values for a single complex number. So in order to get a unique value, we normally pick what's called the principal value of the argument, and that could either be between pi, minus pi and pi, or 0 and 2 pi. And once we do that, we call that the principal branch of the argument. Now, all the arguments, all the different possibilities would be written this way. So argument of z equals the principal branch, which, as I say, is either between minus pi and pi, or 0 and pi over 2 pi, and then plus or minus 2 pi n. So that this gives you all the possible values. In this picture here, on the right, we basically have 2 points. And what I want to show is there's an issue at the transition between the boundaries when we pick a principal branch. Now, if we go with the one we mentioned earlier between minus pi and pi, so right along here where I'm pointing, we have what's called a branch cut. And if you look at the point minus 1 plus I times epsilon, assuming epsilon is some small number, and the point minus I epsilon, which is just a little bit below it, when you take the limit of the one above, it eventually, the argument approaches pi. However, when you take the limit as epsilon approaches 0 of this one here from below, you approach minus pi. So there's a discontinuity. There's no way of getting around that. You can move where how the principal branch is defined. So you can make this cut, along here if you wanted to. In the case where you have the principal branch goes from 0 to 2 pi. But no matter what you do, you're going to have an array of discontinuity for the argument. So this will come up when we talk about multi-valued functions. We're going to sometimes you need to move around the principal branch of the argument in order to avoid this problem, but it does persist. So I would strongly recommend making sure you understand this principle here, this point, before proceeding. There's a shorthand way of writing the polar form of a complex number using the exponential function. And you see it here in theorem 112. And I'm going to prove that in a minute, but I guess I should mention why I numbered this theorem 112. The notes that I'm using, or the book that I'm using to create these slides and these presentations, is a book that I wrote. It has 3 chapters. The third chapter is on complex analysis, which is why the theorem number starts at 112. The book, the electronic version of the book, is freely available, and I'll put the link down below. I encourage you to download that. Most of what's in the slides are in the book and vice versa. So if you want to go back and kind of just read it at a second time after you've listened to the lecture, or vice versa, read the book first and then listen to my lecture, you can do that. And as I say, the numbering is going to start at 112. This is important because when I get later into the course, I may have theorem 125 and I need to point back to theorem 112. So rather than you going through all the different lessons trying to find out, if you have download a copy of the book, I'll consistently use the numbering in the book, and you can just look up any theorem that I reference that way. Okay, now getting to the theorem, it's pretty easy to prove. We let f of theta equal the cosine theta plus I sine theta over e to the I theta, which we can write as e to the minus I theta times cosine theta plus I sine theta. We take the derivative of f of theta. If you recall how that works, it's the product rule. It's the first term times the derivative of the second, which is minus sine theta plus I cosine theta. Then derivative of the first, which you use the chain rule there to get minus I e to the minus I theta. and then times the second term. And interestingly enough, when you reorder these, you notice that they, and keep in mind that when you multiply I times I, you get -1. So these all cancel each other out and you get 0. If the derivative of a function is 0, it must be that the function is constant. And we also know that f of 0 is 1. That's just by plugging in theta equals 0 into this. We know it's 1. And sine of 0 is 0, cosine of 0 is 1. So we get 1 here. And then so f of theta equals 1. And if this thing equals 1 here, then we basically just multiply e to the I theta times 1, and we get our identity. So if you haven't seen this before, it's pretty amazing. Okay, so just plugging that, what we just derived in the previous slide, into the polar form of a complex number, we have z equals r, the modulus, times cosine theta plus I sine theta. That's what we derived previously. And then we just plug in e to the I theta for this expression here, which, as I say, we derived in the previous slide. And this is called Euler's formula. It's very useful. It comes up repeatedly over and over again in complex analysis. And we get the amazing identity here. If we put in pi for theta, we have e to the I theta equals -1. So, pretty much unexpected. You have a transcendental number e to an imaginary number times another transcendental number pi, and you actually get a negative integer. So one of the very interesting things that we run into in complex analysis. Euler's formula can be used to prove various trigonometric identities. We're going to do one example here. If you take e to the 3I theta, which I'm pointing to here, and using Euler's formula, we get cosine 3 theta plus I sine 3 theta. On the other hand, we can write e to the 3I theta as e to the I theta cubed, and then that's, again, using Euler's formula, cosine theta plus I sine theta cubed. If we use the algebraic identity that I'm pointing to up here in the upper right, we can just multiply this out and cube it, and we get this line here. Just remember, when you multiply I times itself, you get a minus, and if you cube I, you get a minus I. So that's the second line. The third line is just taking the two real parts and putting those together, and then taking the two imaginary parts and collecting those together. Going to the fourth line, we use an identity here. We want to get all cosine here on this side. So we substitute 1 minus cosine squared for sine squared. If you remember from trigonometry, sine squared plus cosine squared equals 1. So that gives us this identity here. Then on the right, we have the same issue. We want to get just sine. So we have cosine squared, and we write that as 1 minus sine squared. We multiply things out and get the fifth line in our analysis, this line here. And then we can just identify the real parts with what we had in the beginning. So cosine 3 theta needs to be equal to this real part here, 4 cosine cubed theta minus 3 cosine theta. And then the imaginary part, sine 3 theta, needs to equal this expression here, 3 sine theta minus 4 sine cubed theta. And I'm just listing the identities here at the end. And by the way, I just noticed, and it's kind of annoying, but I made a mistake in the book. There should be a cube here. So if you download the published version of my book, unfortunately, this just says sine theta, but I fixed it here in the lesson. So just a caution if you're working from the book. Okay, we have a few examples for you to try convert the complex numbers shown here, which are in the Cartesian format, and into polar format using the exponential form. And I give you the answers here. You should be able. Two of them we've already kind of worked on. This one here, 1 plus I. If you recall, we had a graph a few slides back, and you just need to read off the numbers from that. And then there's the second exercise is the double angle formula. We did the triple angle formula in the previous slide. This is a little bit easier. You should be able to use the same idea to derive this. In this slide, we go over two of the examples or exercises from the previous slide. The first one is converting the complex number -1 minus I into a polar exponential form. We have -1 is the x coordinate, -1 is the y coordinate. The point is right here that I'm pointing to. Using the Pythagorean theorem, the modulus is square root of 2. In the angle, we measure between minus pi and plus over pi because of we're using that as the principal branch. So we get -3 pi over 4. The angle inside here is pi over 4, 45 degrees. And we just plug that into the formula, so we get the answer square root of 2 e to the -3 pi over 4I. On the right, we have another one to work through. The complex number is square root of 3 plus I. The x coordinate is square root of 3, the y is 1. Using the Pythagorean theorem, we get the modulus is 2. This is with these proportions, square root of 3, 1, and 2. You may recall from trigonometry that that's a 30, 60, 90 degree triangle. The angle of interest is the one here, pi over 6 or 30 degrees, and we plug that into the formula and we get the answer 2 times e to the pi over 6I.